Hi everyone, I'm Sifei from NVIDIA Research. In this tutorial, I will talk about learning visual correspondence across instance and video frames. I will start with the concept, talk a little bit about what is visual correspondence in computer vision with the most common supervised task. First, we have the classification task in relatively the highest level, where the network trying to learn image level correspondence that pins to a specific category, for example, the cat, and we call it the category correspondence. In the mid-level vision, the network instead learns a pixel-wise or region-wise classification, where pixels are pinned to human-defined semantic labels. We also supervisedly learn motion, where the network is able to find dense correspondence between frames. All of these techniques learn correspondence in the supervised manner, where labels are manually annotated to associate the common properties. However, in many applications, we simply need the correspondence themselves. For example, we can use dense correspondence to reconstruct the 3D object from multi-view images. We can also track and edit videos by propagating masks or texture images. For all of this, assigning a human-defined label is not necessary. Labeling correspondence pairs is also quite impossible on large-scale dataset. So in this talk, I want to address the problem of correspondence learning without labels, or say, in a self-supervised manner. So to talk about the background, learning dense image correspondence has a long history and was quite popular in the past 20 years. It is a direct or indirect core technique for many applications, such as 3D shape matching, part propagation in both the 2D and 3D domain, structure for motion, as I have already shown in the previous slides, and also the video stitching, which is quite useful and popular for video editing. So in this talk, besides introducing the core techniques, I will also particularly introduce how to utilize this method for 3D reconstruction. Specifically, I will introduce two aspects of learning correspondence: semantic correspondence, which helps to learn the corresponding part between different instances, and video correspondence, which densely tracks regions or pixels in the time domain. So after that, I will introduce two of our recent work which utilize these two self-supervised correspondence models to perform single image 3D reconstruction, either from a collection of images or from unlabeled videos. Arun had already introduced the details of core part segmentation. Here I will directly move on to the self-supervised single-view 3D reconstruction via semantic consistency. I will also briefly review the scopes in the middle of the talk and trying to connect why and how we use it as a semantic regularization. In this work, the goal is to reconstruct the individual object into 3D meshes without any 3D shape annotation, camera, key point, and template. In other words, we only need a group of images of the same category, and then we can do 3D print for all of them, which is a quite attractive application. Meanwhile, the method also learns a template of one category from scratch. So first, we model instance shape as a deformable mesh. No matter how the shape of each instance is deformed, its semantic part doesn't change. For example, whatever a bird looks like, it always has a head, neck, back, and belly. If we take them as semantic classes, for each face of a mesh, the class label will never change. So if we have a UV space which lies all the faces in a fixed order, then the semantic map on this space is always invariant. So we can use such kind of invariance to help to learn mesh reconstruction. So here is a base network introducing the CMR, which is the most related work. The idea is to input an image and use a reconstruction network to disentangle the texture flow, shape, and camera. The shape is a vertices offset with respect to the predefined template. We use the texture flow to sample pixel values from the original RGB to obtain the texture map, and then we warp it to the shape. Along with the camera, we can render it back to the 2D plan. We can compare both the silhouette and the RGB values to the ground truth. However, we note that in the CMR, both the template and the camera can be calculated. According to our setting, we need to remove it, and if we directly remove this condition from the network, and then the result will be pretty bad, as both the B and C shows. So in this work, we try to address this problem by making use of SCOPS, a self-supervised core-part segmentation method. Essentially, this model is able to learn semantic parts that are consistent between different instances within a specific category. As a brief review, this model is supervised with the geometric concentration, equivariance regularization, and also a semantic consistency constraint, which is trying to perform the spatial clustering. So here I want to note that with the self-supervised learning, each part does not need to have a specific semantic meaning since pixels are clustered in a data-driven fashion. So back to the self-supervised 3D reconstruction problem. If we do not have camera or key points, how can we resolve it? Our solution is to make use of scopes which produce consistent parts for all instances. Remember that we have the texture floor with the 2D domain to the UV space. According to the semantic invariance, all the paths across different instances should be consistent on the UV space. So here we simply enrich all the individual sampled scopes map to formulate this canonic semantic UV map. We found that this canonic map has much better quality than the individual ones, as it rules out the outliers and noises. We can warp it to the estimated shape and compare it back to the original part segmentation in the 2D space through the differentiable renderer. The effectiveness of semantic consistency can be further explained in this example. Once we have a flying bird, it's very likely that the network output a shape and a texture that are highly consistent with our silhouette and RGB values in the 2D space. However, the semantic maps are totally wrong, as the head is warped to the tip of the wings, so we call it camera shape confusion. If we warp the canonical map to the reconstructed shape and enforce it to be consistent with the scopes map in the 2D space, and then this confusion can be easily avoided, and we will have a more meaningful reconstruction result. We also discovered that using an existing template is not necessary, since the template represents the mean shape. It can be progressively updated from a sphere. So, we learned the network and the template in an iterative way. We started from a sphere, and we aggregating the average shape deformation to it for every k epoch until it converges. When we update the template, we first use the encoder to extract the features of alternate samples and then feed the averaged features to the decoder. The output of the decoder is used to update the current template to a new template. Meanwhile, we also update the canonical semantic UV map by averaging the individual UV scopes sampled from each instance image at the same time with the template. The blue boxes run like an aim step in the EN like iterative learning. Here we first show some quantitative results on the bird images. The last two images are actually paintings of bird. We also train our model on rigid objects like cars and motorcycles, which works pretty well. And here we also show some results with respect to some non-rigid objects like zebra, horse, and cows. So finally, I would like to emphasize the key to learn such highly ear-posed problem. Recall that I have mentioned the structure from motion, which deal with the correspondence for one particular instance among multiple views. But here in this topic, we only have one collection of images with totally different instances. So the key is always to find the semantic correspondence that can associate the corresponding regions. So that's why we found the scopes method is a perfect match. And I'd also like to mention that with the learned 3D reconstruction model, we are also able to go back to improve the performance of the core path segmentation itself. Please find the details from the paper. So let's move on to the second part of this talk. Next, I will talk about how to learn video correspondence and how it can help with reconstructing dynamic meshes self-supervisedly from videos. In this work, we learn reliable dense correspondence from videos in a self-supervised manner. Once we have a video, the task we are going to handle here is to learn the pixel-wise or region-wise correspondence among different frames. We treat each pixel or region as a basic visual element. We build a fully connected graph between them, where each visual element is a vertex and the possible correspondence between them are the edges. For each vertex, we model this correspondence by learning the probability with respect to all the possible elements being connected to it. As a result, the probability vector can be with a length of n, indicating the number of vertices or pixels of a frame. In total, we will have an n by n affinity matrix that model this dense correspondence in a probabilistic manner. The element of the affinity matrix describes the similarities between two vertices. The full matrix can be used as a global filter to warp one frame or feature map to another. Alternatively, it can also be used to transform a standard coordinate map, which indicates where the object travels in the next frame. With the basic graph structure, in this work, we propose to learn reliable dense correspondence from video in self-supervised manner. The reason we resort to the self-supervised method is because annotating pixel-wise correspondence between images is almost impossible. On the other hand, the learning of video correspondence would potentially benefit a large number of video applications, which I will show later. So in this work, our learning process will integrate two highly related tasks, object-level matching that tracks large image in the video, and also the fine-grained matching, which establishes pixel-wise associations between consecutive video frames. Although highly correlated, the object-level localization and fine-grained matching tasks are seldomly solved together due to different optimization goals. We demonstrate that these two tasks benefit each other by sharing an affinity matrix that associates the content of two images. The region-level localization helps to localize a patch that is similar to the reference, and the fine-grained matching further enhances the feature representation by the reconstruction loss. Since both affinity matrix and sub-affinity matrix are computed from the same CNN network, when we are learning the two tasks together, they will always progressively benefit the self-supervised representation learning. As a result, we will see both the localization result and the matching of pixels will be continuously improved from the first iteration to specifically, given two frames, we first randomly sample a patch from the first frame while keeping the full target frame. The CNN that learns image representations will output features of both source patch and the target frame. The affinity matrix is computed to represent the similarities between these two feature maps. By multiplying the affinity matrix with the standard grid coordinate matrix, we are able to localize the source patch in the target frame. As shown in the yellow box, the localized patch share common content with the source patch, where we can call this patch as the target patch. We can move on to the fine-grained stage. In this stage, the network learns to warp the color information from the source patch to the target patch. Since the target patch is a local region of the target frame, a sub-affinity matrix can be extracted accordingly. We use the sub-affinity to warp the color channel of the source patch, while difference between the predicted target patch and the ground truth patch serves as the supervision signal. Here, instead of transforming a raw frame, we utilize a pre-trained autoencoder and carry out the transformation in the bottleneck. We reconstruct the target patch features and match it back to the image space by the pre-trained decoder D, and finally, we calculate the objective, for example, the L1 loss between the reconstructed and the ground truth target patch. With the shared affinity matrix as the bridge, the CNN gets gradient from both tasks during the joint training process. Once the feature representation gets improved, we can imagine that there will be a better localization to be obtained, where the color matching can be performed between a better aligned patches. The two stages improve each other and joint benefit the CNN's representation learning in a self-supervised manner. On top of the progressive training framework, there are still existing matching ambiguities that possibly lead to wrong correspondence. Since we use the color or appearance reconstruction as the only objective so far, this gives the model a lot of freedom. For example, one pixel here can be matched to any pixel with similar color. The objective itself does not regularize the local content for matching, which means we need to resort to more spatial regularization to eliminate the mismatches. Because we carry out tracking by propagating individual pixels, we propose a concentration loss, which states that once we crop a local region and transform these pixels to another frame, these pixels should still stay together instead of diffuse apart spatially. This loss regularizes that local content should also match to each other rather than only match to the individual pixels, and once object or local regions are moving over time, they should always move as a unit. We also propose the orthogonal regularization to encourage the cycle consistency. Considering the orange pixel in frame 1, we can map it to frame 2 and then map it back to frame 1. So here we constrain these pixels to always fall into the same location when mapped back to frame 1. And mathematically, we still make use of the affinity matrix by matching features from frame 1 to frame 2 and back to frame 1. And here we have this formulation. Since two frames from the single clip usually have consistent style, well, the style here refers to the second moment statistic, similar to the concept in the style transfer. We also describe it as an energy preservation term between these two features, and by combining these two terms, we can finally reach to the equation showing that the affinity transformation should be orthogonal. So the orthogonal constraints satisfy both the cycle consistency and the energy preservation in videos. It also saves a lot of computation since we can avoid to compute the affinity matrix twice as shown in the left image. Here we show some quantitative elimination studies on the task of instance mask propagation on day 17 using the GME and FP evaluation. The task is to propagate a ground truth segmentation mask from the first frame to the rest, which I will introduce later. We found that by dropping different blocks like localization module, orthogonal constraint, and the concentration constraint, the performance also decreases constantly, which means all these modules, which I have introduced before, contribute to the video correspondence learning. Here we can show some propagation of instance segmentation here on Davis 2017, and we can show that our method can generate quite coherent and complete results. We also found that learned affinity can also handle pixel level tracking across frames. The tracked pose can faithfully describe the pose changes over time. And here we also show another example on human part propagation, which is another application for semantic mask propagation. In this dataset, there's a lot of fine-grained details compared to the instant level propagation. For example, the hair region. We can see that the affinity can also track this small region faithfully with a long duration. So the learned affinity matrix or the CNN self-supervised representation is quite general and can be used to propagate any attribute attached to the keyframe. The general video editing is also a feasible application here, where we simply show to propagate a painting of a random strip texture on videos. So in the last part of my talk, I would like to show a recent work where we try to use the video correspondence as the core technique and use it to do the dynamic mesh reconstruction from videos in the wild. So mostly existing work for dynamic mesh reconstruction rely on strong shape priors. For example, the articulated models to modeling the motion patterns. We have the SMPL model for human body and 3D movable model for dynamic faces. Our work is more challenging in the sense that we do not require such prior knowledge since they may be hard to obtain for wild animals that are hard to be scanned in a controlled environment. In this work, our goal is to reconstruct a non-rigid object instance from, for example, a video of a bird that captured in the wild. We do not assume any non-articulated model. So recent work had successfully trained a reconstruction network for a single-view object instance given a group of training images that are annotated with silhouette and key points. However, when we try to apply the trained image-based model to a testing video, the reconstructed object showed discontinuous shape and flickering camera predictions. The reasons are many. First, most videos we found from the internet is captured by mobile phones. Some of them contain low-quality frames or with small foreground objects. Others show divergent appearance variations such as lighting variance or cluster background. Almost all of them show large domain gap with the image dataset we used for training. One solution is to annotate bird videos as much as possible so that we can retrain the model to cover this gap. However, to annotate video frame-wisely is never easy. It requires extensive human labor, and we cannot guarantee the coherence of the annotation. So how to deal with it? In this work, we propose an online adaptation approach as the solution. We first train a single-view reconstruction network using a group of annotated images. During testing, we fine-tune the network to let it always adapt into a particular video. The difficulty of online adaptation is that we do not have any labels on the testing data, the video. We need to figure out effective self-supervised objectives that can improve the network over time, and here we resort to the temporal consistency. We figure out several important factors with respect to shape, texture, and random parts, which reveals the object's internal properties and agnostic to the shape deformation caused by non-rigid motions. During test time training, we enforce the predictions of those factors to be consistent among different frames of the same video clip. For shape, instead of predicting the coordinate of row vertices, we decompose it as shape-based combination and the offset with respect to it. The shape bases are the shape clustered via KNN from a baseline network. The combination of base reveals the identity of an instance. For example, it can be an ordinary bird, a flying bird, or a duck. And we enforce the prediction of the coefficient, the beta, to be always the same for different frames. Likewise, we also explore such invariance over the UV space, which is independent to the shape deformation and the camera view. We can enforce RGB textures or painted random strips on the UV map to be consistent over time. In detail, we paint random strips only on the first frame and propagate them to the rest of frames using our self-supervised video correspondence learning algorithm. After that, we map the individual part to the UV space, arranging them to have a more reliable part map, and warp it to each predicted shape and render it back to the 2D space. So, by comparing them against the original propagated strips in the 2D space, the shape and the camera can be regularized over time. Finally, we show much more stable and temporally coherent dynamic mesh reconstruction result using the proposed method. Here is another example. We can see much more refined motion details revealed from the dynamic mesh. In addition, we also show that compared with image-based model, where reconstruction is conducted per frame, our method can produce much more coherent camera and mesh evolving over time. We also tried our method in other animals in the wild without articulated models, such as to a walking zebra. That is to say, this work also provides a way to carry out research, for example, the 3D reconstruction, to the endangered species for which scans or other type of labels are difficult to obtain. So, the above content is my talk about the details for both semantic and video correspondence learning, along with their applications to the self-supervised 3D reconstruction and online adaptation of dynamic 3D reconstruction. So in this slide, I want to discuss a fundamental question in the self-supervised learning, which is how to avoid degenerated solution. In image-based 3D reconstruction, since we assume no shape prior in our method, the camera shape confusion itself is a typical sort of degenerated solution. So if we simply predicting camera and shape jointly, well, the part correspondence actually provide a way to resolve this kind of degeneration by providing an implicit regularization to the camera prediction. So this is also similar to the structure from motion, where we simply perform the matching between different instances. According to the video correspondence learning, the degenerated solution usually appears if there is a cycle consistency loss. For example, in our orthogonal regularization, the model tracks pixels back and forth and constrains them to fall into the same location after one cycle. So it is very likely that the model will learn an identity affinity matrix, while pixels always stay at the original locations. In our work, since we also have the frame reconstruction loss and the concentration loss, the degenerated solution can be easily avoided because of them. In several other related work using cycle consistency for video correspondence learning, different augmentations like random cropping from the first frame is applied in order to avoid it. More information can be found from these two papers. As a core technique to computer vision, we believe the correspondence learning and application still has a big room to be improved. As for the future work, one direct intention is to enable a model to simultaneously learn both the semantic and the video correspondence across frames and across different instance images. The outcome is a direct model to deal with the category level self-supervised 3D reconstruction for both images and videos. We also expect that this algorithm will be leveraged into downstream CV tasks to many more self-supervised information from videos, for example, for semi-supervised learning. So this is my talk. Thank you for attending.